In the early 21st century, China did something no human system had done before. It did not send a visitor to the deepest place on Earth. It built the ability to return. For 4 billion years, the Mariana Trench existed in near-perfect isolation, a world governed by pressure, darkness, and geological time. Then a new rhythm entered that silence. Not a living thing, a machine, electric thrusters, repeatable descent, infrastructure. This shift did not add humans to the abyss. It added continuity. The deepest place on Earth stopped being a destination. It became an interface between civilization and an extreme ecosystem that was never meant to be accessed, let alone inhabited. What happens to a frontier when a civilization stops visiting and starts staying? Long before machines, before mammals, before oxygen even fully saturated the sky, a violent wound opened in Earth's crust. It happened when the massive Pacific Plate collided with the Mariana Plate, narrowed and was forced downward, diving into the mantle in a process known as subduction. This collision created the Challenger Deep, a crescent-shaped scar in the western Pacific that plunges nearly 11 kilometers down. Even Mount Everest would disappear beneath more than 2 kilometers of water. This is the Hadal Zone, named after Hades, the kingdom of the underworld. It is for all intents and purposes a planet within a planet. For most of Earth's history, this realm has been defined by absolute exclusion. Here the sun is a distant memory leaving the abyss in perpetual darkness. The water temperature hovers just above freezing, and the environment is devoid of the nutrients that fuel the surface world. Until recently, humanity's relationship with this place was defined by distance and by the limits of every system we built to reach it. We mapped it from space or sent brief probes to touch the bottom and return. The physics of the deep were simply too unforgiving to allow for anything else. But to understand why the current shift is so profound, we must first understand the sheer brutality of the physics that has guarded this gate for eons. Before any nation could study the trench, before any data could be extracted, one force had to be confronted first. The primary rule of the Hadal Zone is simple, yet absolute pressure. At the bottom of Challenger Deep, the ocean exerts a crushing force of approximately 186 bars. To visualize this, imagine the pressure difference between Earth and the vacuum of space, then multiply it by 1,000. But unlike a heavy weight resting on top of you, this force is hydrostatic. It presses in from every direction, simultaneously seeking the tiniest structural weakness to exploit. History gave us a terrifying preview of this power in 1960 during the first-ever descent by the bathyscaphe Trieste. At 9 kilometers down, a loud, violent crack echoed through the hull, shaking the vessel. It wasn't a collision. It was the plexiglass of an outer viewing port fracturing under the stress. The explorers Don Walsh and Jacques Piccard continued, but the ocean had made its point. In this domain, the margin for error is zero. If a human were to step outside at this depth without protection, the result would not be the dramatic explosion often seen in cinema. It would be far more visceral. It would be a rapid, catastrophic collapse. The air inside your body would be compressed to a fraction of its volume, collapsing the body inward. You would not drown in the traditional sense. You would be physically condensed by a hydraulic vice that never relents. We can see this violence in objects sent down as demonstrations. A standard styrofoam coffee cup attached to the exterior of a submersible returns to the surface unrecognized. It is not torn apart. It is shrunken white and hard as rock, compressed to the size of a thimble. The air pockets that gave it structure have been squeezed out, leaving only the deformed plastic skeleton. This is what the ocean does to anything that refuses to adapt. China's deep-sea program exists for one reason: to build machines that can. And yet, something down there already has. At these depths, even the water itself begins to behave strangely. We are taught in school that liquids are incompressible, but under 1,000 atmospheres that rule bends. The water at the bottom of the Mariana Trench is compressed by about 4.6% relative to the surface. The molecules are packed so tightly that the density of the medium changes, altering its thermodynamic properties. This compression turns the water into a potential weapon. According to Pascal's principle, pressure applied to a confined fluid is transmitted undiminished. If a hairline fracture were to open in a submersible's hull, the water wouldn't just leak in, it would jet through the breach with the cutting power of an industrial laser slicing through machinery and flesh alike before the hull ultimately buckled. It is difficult to overstate how hostile this environment is compared to the rest of the solar system. Consider Venus often called the hell planet due to its crushing atmosphere. On the surface of Venus, the pressure is about 92 bars. In the Challenger Deep, it is nearly 12 times that amount. We have sent landers to Venus that survived for only minutes. Sending humans to the bottom of our own ocean is, in terms of sheer physical stress, a greater engineering challenge than walking on the surface of our celestial neighbor. For billions of years, this extreme physics acted as a perfect barrier. It ensured that the trench remained an exclusion zone, a sterile scar where nothing fragile could survive. Or so we thought. Because when we finally peered into the darkness, we didn't find a desert. We found life staring back life that had solved a problem physics said was unsolvable. Physics draws the first line. Biology is where the real battle begins. The existence of the Mariana snailfish, scientifically known as Pseudoliparis swirei, is a biological provocation. At depths exceeding 8,000 meters, complex life faces a molecular crisis. Under extreme pressure, surrounding water intrudes into protein structures, causing them to misfold and fail. Yet the snailfish thrives here. Translucent, scaleless, and fragile in appearance, it glides through the abyss with a ghostly ease. Its secret lies in a potent chemical defense called TMAO, short for trimethylamine N oxide. Think of TMAO as molecular pillars holding up a roof. Inside the fish's cells, these molecules bond with water, creating a structured framework that prevents the crushing external pressure from deforming vital proteins. It is an evolutionary masterpiece of biochemistry. However, evolution has a ceiling. To survive deeper, a fish requires higher concentrations of TMAO. But there is a limit at approximately 8,200 meters. The necessary concentration of TMAO would make the fish's cells more salty than the seawater outside. This would cause a fatal osmotic imbalance. The cells would swell and burst or cease to function. This depth marks what biologists call a biological wall, a theoretical limit beyond which fish physiology fails. Beyond this wall, the trench belongs to the microscopic, and what lives there does not play by the rules of surface life. Where vertebrates falter, the microbial world explodes in diversity. To observe this hidden world requires access not just once, but repeatedly. Recent expeditions have not just found life, they have uncovered an entire shadow biosphere operating on alien logic. Deep in the sediment of the Challenger, deep at 8,900 meters, scientists isolated a new viral entity, VBER H-AIM H4907. This bacteriophage does not behave like the aggressive surface viruses we are familiar with. In the resource-starved darkness, killing your host immediately is a suicide mission. Instead, this virus is lysogenic. It infects a bacterium, inserts its genetic code into the host's DNA, and waits. It replicates quietly as the host divides a patient predator, sleeping inside the prey, surviving generation after generation until the moment is right. This is just one data point in a flood of new information. Through projects such as the Mariana Trench Environment and Ecology Research Program known as Mere Chinese Submersibles have retrieved thousands of sediment samples identifying over 7,000 microbial species, most of which were previously unknown to science. These samples represent more than just biological curiosity. They are the genetic blueprints for survival in hell. They contain enzymes that function at freezing temperatures and high pressures, a holy grail for industrial biotechnology and synthetic medicine. As these expeditions return again and again, their laboratories accumulate the world's largest archive of Hadal life. In practice, this places China at the center of humanity's interface with this new tree of life. But as we catalog these ancient biological secrets, we are also discovering that we are not the first visitors here. Long before the submersibles arrived, something else from our world had already claimed the bottom, something far smaller and far more permanent. The deep did not wait for us to arrive. We reached it long before we meant to. The first ambassador humanity sent to the Challenger Deep was not a brave explorer or a cutting-edge robot. It was a single strand of polyester. When scientists began dissecting Hirundalea gigas, the dominant scavenger amphipod of the trench, they expected to find traces of ancient organic matter, the scraps of marine snow that drift down from the surface. Instead, inside the digestive tracts of these shrimp-like creatures, they found bright blue and red tangles of synthetic material. In one landmark study of the Mariana Trench, every amphipod sampled contained microplastics. This discovery shattered the illusion of the deep ocean as a pristine sanctuary. We realized that the trench is not just a biological frontier, it is the planet's ultimate sink. Gravity acts here as a relentless funnel, pulling fragments from the surface into the deepest cracks of the crust. Geologists have a term for what we are creating down there. They call it Anthropocene stratigraphy. If it is not swallowed by tectonics, a future observer will one day see a thin band of compressed plastic marking our era. For decades, this was our only contribution to the Hadal Zone, a passive, accidental rain of debris. That era of accidental presence is over. The passive drift of plastic has been replaced by the active thrust of propulsion. We are no longer just contaminating the trench from afar. We are building the capability to descend into it, inspect it, and perhaps exploit it. The arrival of plastic proved that the surface world touches the bottom. The arrival of machines proved that the surface world intends to stay. And staying here requires a kind of engineering we had never built before. This is where exploration stops looking like curiosity and starts looking like infrastructure. To understand the leap China has taken, we must look at the shape of the vessel. In 2012, when filmmaker James Cameron descended to the Challenger Deep, he did so in the Deep-Sea Challenger, a vertical, torpedo-shaped craft. It was an engineering marvel built for speed, plunging rapidly to the bottom and shooting back up. But inside, Cameron was cramped in a steel sphere barely wide enough for one man's shoulders. It was a vehicle built for a sprint. China's submersible Fenduze, whose name means strive, was built not for a record, but for repetition. At its heart lies a massive titanium alloy sphere, nearly 2 meters in diameter. The choice of a sphere is a matter of survival geometry under uniform hydrostatic pressure. A sphere distributes stress evenly across its entire surface. There are no corners to crush, no flat planes to buckle. But building a sphere large enough to hold 3 people, a pilot, and 2 scientists while withstanding $1,000 atmospheres is a materials science nightmare. Steel. The traditional choice is too heavy. To make a steel sphere thick enough to survive 11 kilometers, it would become an anchor unable to return to the surface under its own buoyancy. The solution was a specialized titanium alloy, often described as Ti62A, engineered specifically for high compressive strength and ductility. Constructing this hull required a manufacturing breakthrough. You cannot simply bolt plates of titanium together. The bolts would be weak points, shearing instantly under the pressure. Instead, Chinese engineers utilized a technique known as electron beam welding, or EBW, inside a vacuum chamber. This technique melts the edges of the titanium hemispheres, fusing them into a single, seamless monolith. The tolerance for error was sub-millimeter. If the sphere deviated from perfect roundness by even the width of a few human hairs, the uneven pressure distribution could lead to a catastrophic collapse. This kind of manufacturing does not emerge from a single lab. It emerges from an industrial ecosystem. The result is a titanium lung, a bubble of air that keeps 3 humans alive, comfortable, and working in an environment that should kill them. Unlike previous vessels where the pilot was essentially trapped in a fetal position, Fenduzi allows a team to operate robotic arms, process samples, and conduct complex experiments. It is not just a survival capsule, it is a mobile laboratory and part of a larger logistical machine. But infrastructure is not defined by what it can do once. It is defined by what it can do every day. However, the true innovation is not the ship itself. It is the system behind it. For 60 years, reaching the Challenger Deep was a moonshot, a rare singular event. The Trieste touched down once in 1960. Cameron touched down once in 2012. These were historical anomalies separated by decades of silence. They proved it was possible to survive the trip, but they did not establish a presence. China has changed the paradigm from event to cadence. Since its deployment, Fenduze has not just visited the trench, it has commuted there. Supported by dedicated motherships and rapid launch and recovery protocols, the submersible has conducted hundreds of dives across the world's deepest trenches. with a heavy concentration in the Mariana. In a single expedition, it can dive day after day, cycling crews and equipment with an industrial rhythm that no other nation currently matches. This is the difference between a stunt and an institution. By turning the descent into a routine operation, China has crossed a critical threshold. They have moved beyond the phase of access, the ability to get there, and entered the phase of permanence. When a nation can place scientists on the seafloor as easily as it sends commuters on a train, the nature of the territory changes. It stops being a remote wilderness and starts becoming a managed resource. And the first step in managing any territory is to map it. The second is to name it. No frontier is ever shaped by one actor alone, but every frontier is eventually shaped by one system. To understand the magnitude of this shift, we need to widen the frame. China is not the first nor the only nation to unlock the secrets of the deep ocean. In fact, the history of the abyss is written largely in English and Japanese. The United States pioneered deep submergence. The Trieste was a U.S. Navy triumph. The legendary DSV Alvin, operated by Woods Hole, has logged thousands of dives discovering hydrothermal vents and reshaping our understanding of biology. Japan's Shinkai 6500 has spent decades meticulously mapping the seafloor and studying seismic faults. These programs are scientific gold standards responsible for the vast majority of what we currently know about the ocean. But there is a critical distinction in mode of operation. Historically, the great achievements of exploration appear as brilliant sparks, intense, illuminating, but intermittent. Trieste went to the bottom once and never returned. Deep-sea Challenger went once. Even the workhorses like Alvin and Shinkai operate primarily at abyssal depths, reaching only about 6,500 meters, leaving the deepest portions of the ocean, the Hadal Zone, out of reach for routine operations. China's approach is different. It resembles less a spark and more a steady industrial hum. By building a fleet of full ocean-depth submersibles like Fenduje and supporting them with dedicated infrastructure, they have filled the gap that other nations left open. While the West focused on maintaining its aging but reliable fleets for shallower depths, China built a system specifically designed to occupy the absolute bottom. This is not a story of heroes and villains. It is a story of differing strategies. One model views the trench as a destination for specific high-value expeditions. The other views it as a territory for continuous operation. And as history shows, those who operate continuously in a frontier are usually the ones who end up naming it. And once you operate continuously, you begin to formalize what you know. In the age of discovery, explorers claim territory by planting a physical flag on a beach. In the information age, you shape territory by planting a name on a map. This is the quiet power of taxonomy. As Chinese expeditions systematically crisscross the trench, they are doing more than just looking. They are measuring using high-resolution multi-beam sonar. They are discovering seamounts, ridges, and valleys that no human eye has ever seen. And with discovery comes the privilege of naming. Through international bodies such as the Subcommittee on Undersea Feature Names, known as SCUF, and new names are being written into the official geography of the ocean floor, names drawn from Chinese poetry, mythology, and science. This process builds what sociologists might call cognitive infrastructure. It is a subtle form of de facto influence. When future scientists from America, Europe, or India study the Mariana Trench, they will rely on bathymetric data collected by Chinese sensors using maps populated by Chinese names. Whoever sets the standards for the data becomes the architect of the reality everyone else operates within. Once a dataset becomes the default reference, it becomes invisible and therefore powerful. But maps are never neutral documents. A high-resolution topographic map of the Challenger Deep is scientific data, yes, but it is also a strategic asset. The same detailed understanding of salinity gradients, thermal layers, and acoustic shadows that helps a biologist find a rare snailfish also helps a submarine commander hide a vessel from detection. In the deep ocean, environmental knowledge is synonymous with military transparency. By illuminating the dark for science, we inevitably illuminate it for strategy. The trench is being transformed from a void into a known quantity, a digitized environment where terrain familiarity creates strategic leverage. Every system eventually demands a justification. As we watch this transition from the sporadic visits of the past to the digitized, standardized grid of the future, it is necessary to pause. The Mariana Trench is no longer out there. It has been brought into the fold of human affairs. The sheer difficulty of reaching it is no longer a sufficient barrier to protect it. For the first time in history, the protection of this ecosystem relies not on physics but on policy. We stand at a crossroads of intent. Is this permanent presence the beginning of planetary stewardship, where we monitor the health of the ocean's basement and protect its genetic libraries? Or is it the prelude to ownership, a race to carve up the seabed for polymetallic nodules and rare earth elements? The machinery is already in place. The maps are being drawn. But the moral framework for how to handle the last wild place on Earth remains unwritten. We have proved we can stay. The only question left is why and for whom. Every system eventually creates its own point of failure. It is easy to imagine our digital world floating in the cloud intangible and weightless. But the reality is far heavier and wetter. Roughly 99% of all international data traffic, trillions of dollars in transactions, diplomatic cables, military orders, and personal messages travels through physical tubes resting on the ocean floor. These cables are the nervous system of modern civilization, yet they are shockingly fragile. In shallow waters, cables are armored against shark bites and ship anchors, but in the deep ocean, to save weight and cost, they are stripped down. A typical deep-sea fiber optic cable is only about the thickness of a garden hose. Inside, the glass fibers carrying the world's information are as thin as human hair. For decades, the extreme depth of the trench acted as a natural shield. The cables running near or across these abyssal plains were safe simply because they were unreachable. No saboteur could touch them. But the arrival of reliable deep-diving submersibles has evaporated that security. The risk here is not necessarily an act of violence involving explosives. It is far more subtle. A submersible equipped with a simple mechanical cutter or even a manipulator arm can sever a cable at a depth of 4,000 or 6,000 meters. There is no explosion, no sonar signature, just a silent snap in the dark. If a strategic choke point, a location where multiple cables bundled together, were targeted, the result would be systemic shock. Traffic would attempt to automatically reroute, but the remaining cables would be instantly overwhelmed. The global internet wouldn't necessarily go black, but it would seize up. High-frequency trading would collapse due to latency. Satellite backups would be saturated, military coordination would stutter. The pattern is familiar. In 1859, a solar storm burned the world's telegraph lines. Experts often warn of a second Carrington event coming from the sun, but we now face a similar threat rising from the abyss. The difference is that a solar storm is an act of God. A severed cable at 6,000 meters is a demonstration of capability. The mere existence of the technology to reach these depths changes the calculus of global security. The deepest places on Earth, once the safest, have become the soft underbelly of the global network, an exposed nerve waiting for a touch. The deeper we go, the more surface level our problems become. The Mariana Trench was the last place on Earth where humanity was truly absent. That absence is now history. The technological barrier has finally fallen, and with it the luxury of ignoring what happens in the dark. In the coming decade, this silent world will become loud with debate. Will we treat the Hadal Zone as a common heritage, a sanctuary for the unique biology that holds the secrets of life, or will we treat it as a resource to be optimized, a corridor to be managed? The submersible Fenduzo and the systems that follow it have forced us to face these questions sooner than we planned. We have cracked the shell of the planet. We have brought our plastic, our politics, and our ambitions to the very bottom. We change the deep simply by arriving. Now, whether we intend it or not, the deep will change us.